All right, we have a lot to learn today, but it's lots of nice little like theorems and tricks, life hacks for handling polynomial functions. This first one, I just want to talk about the types of zeros, or the types of, we could think of them as x-intercepts, but basically, when do polynomials equal 0? And this is pretty well factored, and so if I set each factor equal to 0, I'm going to be able to find a bunch of zeros here. So I've got x equals 4 is going to be one of my zeros. Subtract the 3, divide by 2, x equals negative 3 halves. This one, add the 2 and take a square root. I'm going to actually get a plus or minus the square root of 2. And same deal on this one, subtract the 16, take a square root. I get plus or minus, and this one's imaginary, yeah? So I just want to talk about the different types of roots that we can get, different types of zeros. And you can see that these first two that I got are rational numbers. They can be written as fractions. So it's possible to get rational zeros. And we also could get decimals. They're kind of yucky. Square root of 2, 1.7, blah, blah, blah. So that's an irrational number. I have 2 rational, 2 irrational, and in this case I had 2 imaginary. So you can also get complex zeros. And a fun fact is that complex zeros come in conjugate pairs. That's like if you had 3 plus 2i as a 0, you would be guaranteed that 3 minus 2i would also be a 0. So in this case it's 0 plus 4i and 0 minus 4i. So just know that you can have a combination of rational, irrational, and complex zeros. All right, so there's this theorem called the rational zero theorem, and it can help you find the rational ones, not the irrational or complex ones, but it says that if polynomial has integer coefficients, so there's one catch, and p over q is a rational zero of f of x, then p is a factor of the constant term and q is a factor of the leading coefficient. So the way that we use this is we look at the constant term and we think of all of the factors p of that number. So what are all the factors of negative 10? We could have a combination of positives and negatives, like positive 1 and negative 10, or negative 1 and positive 10, but we're just going to list out all the possible factors of negative 10, including the negative ones. And then q would be all of the factors of the leading coefficient. So we'd have factors of 2. And then the theorem is saying that if this guy does have any rational zeros, which it might, they would be of the form p over q. So let's make a list of p over q's. So I could take the 1 over 1 and the 1 over 2, or the 2 over 1, or the 2 over 2. So I'm just going to start listing those. So the 1 over 1, or the 1 over 2, the 2 over 1, or the 2 over 2 would just be 1. So I'm not going to list that one again. I've got 5, so 5 over 1 and 5 over 2. And 10 over 1, and 10 over 2 would be 5, so I'm not going to list that again. So this is what they would call a list of all possible rational zeros. If this polynomial has a rational zero, it would be in this list. And the way we would use that theorem is in a problem like this: list all possible rational zeros of this polynomial. So we'd be looking at factors of negative 6 and factors of 2. So the negative 6 would be all of these, and q. And then we would need to stack them. So we're going to stack and make a list of the p's over the q's. So 1 over 1 and 1 over 2. 2 over 1 and 2 over 2. 2 over 2 is the same thing as 1. 3 over 1 and 3 over 2. 6 over 1. And 6 over 2 is 3 again, so I don't need to list that again. So here's my list of all possible rational zeros. If this has a rational zero, it's in that list. And we would like to find all the zeros of f of x. So this is the best bet we have to narrow it down right now. Like, if there's some square root of 2 zeros, I don't know how I'm going to figure them out, but for right now, these rational zeros is what I'm relying on. And the way that I can see if I have a zero or not is through synthetic division. And so what do you have a good feeling about? You think that -1's going to work? So we're just going to pick from the list, and I'm going to try the -1 and see how my luck is today. Not great, not looking good. I did not remember that the remainder would be the value of the function. So we just found out that f of -1 equals 8. I would not consider that an x-intercept. That is not a zero. So I might try again. What do you have a good feeling about? I'll try the +2. No good. And then if you get tired of just guessing and checking, you could always do a little cheat and just actually graph this equation. And when I graph this function, let me zoom in here, what kind of zeros do I see? I'm seeing some maybe fractiony one there, some maybe fractiony one here. This one kind of looks like it's hitting right at the 1, 2, 3 mark. So I think I might try 3 next. And it was a winner. So that just kind of saved me some time. So if you want to look at the graph to at least narrow down that list a little further, that's good. It said to list all possible rational zeros, which I did. I found at least one rational zero. One rational zero is 3, but I want to find all the zeros of f of x. So let's remember how this would factor now. I've got to factor in f of x minus 3 for sure. And these leftovers here tell me that I would have 2x squared plus 6x plus 2 left over. And so maybe I can factor that some more and figure out what those other 2 intercepts were. I would factor out a 2, I think. I don't think I can factor that anymore. So how am I going to figure out the other zeros? I could use the quadratic formula, right? I know where this one equals 0, but I don't know where this one equals 0, and that's really what I need to figure out. So let's throw that into the quadratic formula. Okay, so that kind of explains why I couldn't factor that one, because these other 2 zeros are definitely irrational. They've got a square root of 5 involved. So I think I did find all the zeros, right? So all the zeros would be x equals 3, x equals -3 plus the square root of 5 over 2, and x equals -3 minus the square root of 5 over 2. But it was really that rational zero that helped me narrow it down and then figure out the other two missing zeros. We talked about the factor theorem last time, that if you find a zero, that means you've also found a factor, or if you have a factor, then you know a zero. So we're going to use that and kind of the same process to figure out what all the zeros of this polynomial are. So I'm pretty sure I could synthetically divide out a 2 right now, because they are telling me that x minus 2 is a factor. So let's do that. They weren't lying. If you get a remainder of 0, we know that that was a true 0. And so x minus 2 was a factor. And we're going to use the result to find all the zeros. So we know that these leftovers now represent basically what's left when you factor out an x minus 2. In this case, it would be a 2x cubed plus x squared minus 16x minus 8. And then I have to consider what kind of zeros I can get out of here. So if I needed to throw down the rational zero theorem again, but I am thinking maybe I'm going to be able to factor this one by grouping. That worked well. All right, I think I'm ready to list all the zeros. So kind of knew about x equals 2 already. Also got one at negative 1/2. And this one's going to give me square root of 8, so plus or minus the square root of 8. Or if you want to be fancy, 2 square roots of 2. So this time we got 2 rational zeros and 2 irrational zeros, but we did find all the zeros of f of x. All right, here are 2 theorems that sort of go together. The fundamental theorem of algebra says that if f of x is a polynomial of degree n, then the equation f of x equals 0 has at least one complex root. More commonly understood that the number of roots equals the degree. So that'll help us kind of have a target for how many different roots or zeros we're looking for. And then the linear factorization formula is a natural kind of corollary with it. An nth degree polynomial can be expressed as the product of a constant and n linear factors. Again, if the degree was, say, 7, then you would be able to write it as 7 linear factors. So let's look at that in this context. So do you remember this problem from the first slide? We had 6 zeros altogether, some of them rational, some of them not. But this is only 4 factors, did you notice? And I was promised that if there were going to be 6 zeros, if this is a polynomial of degree 6, I should be able to write this as 6 linear factors. And I can already see that I don't really have linear factors here and here. Those are quadratic factors. So far I do have 2 linear factors. And then, do you remember how this factor right here gave me roots of plus or minus 2? Well, technically I could then write that as x minus the square root of 2 and x plus the square root of 2. We don't normally factor that way, but in order for this factorization theorem to work, it says that we can write those as linear factors too. And then the last factor had zeros of plus or minus 4i. And so to fit the theorem, we could say x minus 4i and x plus 4i are linear factors. So definitely we don't normally factor with imaginary numbers, but we certainly could, and that shows that the linear factorization theorem holds, because if you have 6 zeros in a degree 6 polynomial, you should have 6 linear factors. Okay, a different type of problem using that same theorem. Let's write our own third degree polynomial that has zeros at 5 and 2i. And when you plug in an x equals 1, you should get a 40. So we're just going to write our own polynomial. And it says that it's a third degree polynomial, but then it only lists 2 zeros, and that's a problem because the fundamental theorem of algebra says that I'm going to need 3 zeros. Well, here's the catch. Remember how those imaginary or those complex zeros come in pairs? So if we have 0 plus 2i as a 0, then 0 minus 2i would also have to be a 0. So this indicates that I actually know there is another 0 at negative 2i. So then I think I can write down a little polynomial. And it's got 3 linear factors: x minus 5, x minus 2i, and x plus 2i. And the only catch is, like, there could be a number out in front, and so I'm just going to call that number a. And that's actually going to be important because, remember, when I plug in an x equals 1, I'm supposed to get a y value of 40. So that's kind of the next step, is I want to see what happens when I plug in a 1 for each of these x's. So here I'd get 1 minus 5 is negative 4. This is kind of a nightmare. Can we deal with that? So let's say we FOILed this out. If we FOIL this out, I'd get an x squared plus a 2ix minus a 2ix minus a 4i squared. The 2ix's are gone. Remember how I squared is negative 1? So really this whole shebang is the same thing as an x squared plus 4 factor, which I think makes sense, because if you set that equal to 0, take a square root of it, yeah, that would make sense. Anyway, that's easier to plug a 1 into. Do you remember what we were doing? We were trying to plug in an x equals 1 to get a y value of 40. So let's use this version of that factor. Plugging in an x equals 1 squared plus 4 is 5. All right. So as it is, it doesn't equal 40. So I'm just going to need to throw in an a value. If I divide both sides by negative 20, that convinces me to use a negative 2 for my a. So I think I've accomplished the task. I can write this as negative 2 times x minus 5, and I'm just going to write that as x squared plus 4. So there's a beautiful polynomial that has all the zeros that I wanted and has a y value of 40 when I plug in a 1. I could leave it like that, but let's FOIL it out. So let's FOIL these two together. Distribute that negative 2. We came up with a beautiful third degree polynomial that fits all the criteria. I realize this section is kind of a marathon, but we have one more big thing that we have to learn about. It's called Descartes' rule of signs. And it's useful if we're trying to find the real zeros. Remember, the rational zero theorem helped us find the rational ones. This will actually help us figure out more about even the irrational ones. So this is just about the real zeros. says if we have real coefficients, they don't even have to be integers, they could be fractions or even crazy irrationals, I mean, the number of positive zeros. So we're just kind of narrowing it down to how many positive zeros could this have. The number of positive zeros is the same as the number of sign changes of f of x or fewer by a multiple of 2. Let's look at what that means. So here's an example. The number of sign changes, what they're talking about is like this is a positive 2, that's a minus 16 and a minus 6. So if I were to look at, this counts as one sign change, and then this doesn't change signs. So I only have one sign change in this polynomial. And what that tells me is that I will have one positive 0. Not 3, not 4, not none, but 1. About that thing where it talks about fewer by a multiple of 2. Let's look at this second example. So let's look at our sign changes. This one's positive, so positive to a negative counts as one sign change. Here's another sign change, and positive to negative again makes another. So this one has 3 sign changes. And that doesn't tell me that there's 3 positive zeros. It tells me that there's either 3 or fewer than that by a multiple of 2. So there's either 3 or 1 positive zeros to this polynomial. So that would help us narrow down even if we were doing the rational zero theorem. Like on this one, once I found 1 positive 0, I could quit the positives. Let's talk about the second part. The number of negative zeros is the same as the number of sign changes of f of negative x, or fewer by a multiple of 2. So for this part of the theorem, we have to look at what f of negative x would be. So I'm just going to stick in negatives for each of the x's here. And simplify. A negative cubed is still a negative. This will turn into a plus 16x and a minus 6. So now I'm going to look at these sign changes. So this goes from negative to positive, and then positive to negative. I'm counting 2 sign changes. So what that tells me now is that I have 2 negative zeros. Oh, back up. Or fewer by a multiple of 2. So I could have 2 or 0 negative zeros. Either there's 2 or there's none. Let's try that on the second polynomial. I have to check f of negative x. Negative to the 5th would be a negative to the 3rd would stay a negative. A negative squared is a positive. And let's check the sign changes. So I went from negative to positive here, staying positive, and then from a positive to a negative here. So I'm counting 2. So there are either 2 or 0 negative zeros. By the way, if you would have had like something like 5 sign changes, it would have been 5 or 3 or 1. That's what they mean by fewer by a multiple of 2. We made it to the final example. So we're going to bring together all of our theorems and little rules that we learned and just practice on this polynomial. We're going to find all solutions to this equation, which is basically the same thing as finding the zeros of a polynomial. And we are going to try to use all of the things we learned. So the rational zero theorem was where you take the p's over the q's to narrow down what could be a rational zero. So in this case, we've got the p's would be factors of 4. Q's are factors of 1. And if I start stacking those, I get plus or minus 1 over 1, plus or minus 2 over 1, and plus or minus 4 over 1. So only 6 numbers that could be rational zeros this time. All right, using Descartes' rule of signs, let's check for the sign changes here. So in the original, do you notice everything's positive? So that makes 0 sign changes, which means there are 0 positive zeros. And how many negative zeros are there? So now we're going to imagine that we're sticking negatives in for each of those x's. Well, negative x to the 4th would stay positive. Negative to an even power is positive. And the next one would turn out negative if I were sticking in a negative x. The next one, negative x squared, is just x squared. This one would be a minus, and then we just have the plus 4. So let's count the sign changes on there. It looks like 1 sign change, 2, 3, 4 sign changes. So for the negative zeros, I'd have 4 or 2 or 0 negative zeros. And you might be thinking, okay, well, if there are 0 positive zeros, don't there have to be 4 negative zeros then? Remember, we could, though, have imaginary or complex zeros. So this is only talking about the real zeros. We're going to use the fundamental theorem of algebra and the linear factorization theorem to try to find all of them. And remember that the fundamental theorem of algebra says that all solutions should total up to 4 solutions here. I should be able to find 4 solutions of this equation. And kind of my starting point has to be hoping that there's a rational zero. So I'm going to test my luck here and see if I can find any. Now I could go to the graph and kind of cheat my way out. Do you have a good feeling about any of those 6 numbers? I'm going to try the negative 4, maybe because I have some insider info. Yeah, I had some insider, so I found one of the 4 zeros that this has to have, and it happened to be a negative, which I guess that was sort of expected, right? I wouldn't even have bothered trying any of those positive ones because there are no positive zeros. So the negative 4 is one of my 3 choices. The negative 4 worked. How do we find the other 3? We kind of go back to like the factoring, right? So right now I've got this guy factored as x plus 4. And then all of this leftover stuff. Remember, this is the number, the x squared, the x cubed. And if I had any hope left in any of those other rational zeros, I might try to divide out a -1 or a -2. But this one, actually, it looks like I could factor it using grouping. So I think I'm going to take that shortcut. All right. And if I were to want to factor that, remember I was hoping for 4 solutions. I could split this up a little more, but if I'm just looking for the zeros, I think I've got them. I've got x equals -4, I've got x equals -1, and even though this isn't a linear factor, if I set that equal to 0, x squared equals -1, I'd be taking the square root of -1, and my two outcomes would be plus or minus I. And look, that came in a pair, right? If you have a positive one, you have a negative one too. And so here's my 1, 2, 3, 4 solutions to that equation. So all of these little rules kind of go together to help us find all of the zeros or all of the x-intercepts. I guess if they're complex, they don't show up as x-intercepts on the graph, but we call them roots or zeros. I hope you learned something.